Okay, thank you. Well, first thing I, of course, should say it's a great honor and my great pleasure to be here, and thank Laura, who's just stepped out of the room, and Katie, and the organizers for this great meeting. What I'm going to tell you about today is an idea I've been looking at for several years now, but it may be unfamiliar to most of you, so therefore I'll spend a little time with the background. So there's a paper that goes back to 2001 when we first proposed this idea, published in 2004. There's a review article in 2010, but the work I'll talk about today is actually really quite remarkable. I feel it's remarkable, I hope you agree, is that this idea of a condensate, or P equals minus rho interior to a black hole, which is therefore not a black hole in the same sense, hence the quotation marks, that this idea is actually inherent in the second paper of Schwarzschild back in 1916. So that's what I'm going to tell you about today mostly. So I think I'll skip most of this. You all know this. Classical black holes, of course, have infinite tidal forces and a true curvature singularity at the origin. If I take the simplest possible case, the Schwarzschild spherically symmetric case. Does this work? Yes. However, there's something new in general relativity. The singularity at the origin is, of course, the same kind of singularity you get in electromagnetism with the Coulomb potential, but there's something new in general relativity, which is an event horizon where light rays cannot escape, and this is, of course, why we call it a black hole. And the thing I just want to emphasize is the change of sign of the metric functions as you go through the horizon is, of course, true if I have no stress tensor there, and this is just the property of the vacuum solution. Even in classical relativity, before we talk about quantum effects, of course I could have a sheet of radiation moving on the null surface at the horizon, and that would potentially change what's happening inside. So I just want to emphasize this obvious point that the solutions to Einstein's equations depend on the sources, and what we call a black hole is dependent on having nothing going on the horizon. Okay, now again, you're all familiar with this, that's why we're here, but the issues that come when you try to put quantum mechanics into this is a fascinating interplay of quantum mechanics, thermodynamics, and general relativity. But I just want to call your attention to how striking and paradoxical these questions really are. If you come, walk in off the street and someone tells you that this solution to Einstein's equations has an entropy, if he or she has taken first year classical mechanics or electrodynamics, they say, well, if you have a Coulomb solution, does that have an entropy? Well, of course not. It's a single classical solution to very simple equations, and it doesn't, you don't associate any entropy with it. But as we all know, there are no Hare theorems in general relativity, which tell us if we throw things into this horizon, we end up with only a few parameters, mass, angular momentum, charge, and therefore, in some sense, one has lost all information or data about what one has thrown in. And so in some sense, there seems to be an entropy associated with this object. And Bekenstein, of course, suggested, it's too bad that he has passed away just before this meeting, but he suggested this very novel idea that the area should be associated with entropy, based basically on classical ideas about the increase of the area from dropping in classical matter. Area is always going to increase. Of course, again, I want to draw your attention to a very trivial, obvious thing that is sometimes not said, but should be, and that is that area is not entropy because it doesn't have the right units. So I have to divide by something of units length squared in order to get something which is dimensionless, and then multiply by Boltzmann's constant to get an entropy. So what length squared should you use? Well, there isn't any in classical relativity, and so the only thing you can think of doing if you're starting from scratch here is to divide by the Planck length. If I have h bar in the problem, now it's suddenly entered the problem. All of this was just classical, but as soon as I introduce the Planck length, of course I have h bar, and now I can talk about something at least which has the dimensions of entropy. And this was basically Bekenstein's suggestion, which was certainly difficult to understand just on that basis, where that entropy came from. Then, as we all know, Stephen had this revolutionary paper in 1974 arguing that a thermal spectrum comes out of a black hole, and once you have the temperature, then, of course, the corresponding canonical thermodynamic variable is the entropy, and you can write a classical relation, which is that relating the surface gravity, the area, and the energy, which is just this relation. You can rewrite it in terms of the Hawking temperature and the Bekenstein-Hawking entropy this way, and fix the constant in the entropy, which is the famous 1/4. So it's 1/4 of the area in natural units. I want to emphasize, I mean, we don't, we're so sophisticated, we don't usually write all the units in, but maybe we shouldn't be, because something pretty non-trivial has happened here. You started with a classical relation, and you've really just multiplied and divided by a factor, which includes h bar, and now interpreting this as a quantum formula. So one has to be very careful here as what exactly is going on. So we usually just put h bar to 1, right? Now, as you all know as well, so this is the part of my talk about what's the matter, what's the quantum matter with black holes, is you all know there's a list of problems. So I won't, we're here to discuss these problems, but just the list is, as people have pointed out repeatedly over the years, if you follow the Hawking quanta back to near to the horizon, you will be, just because things redshift coming out, if you go back, they blue shift, and eventually you're talking about frequencies which are in principle infinitely large and bigger than the Planck scale. So that's one issue. Should you believe the semi-classical approximation, and that applies to particles or quanta of that frequencies on a fixed background? Second thing is, we've talked about also for 40 years essentially, is this area formula is fascinating, but it's also very peculiar. If you talk to other physicists in other fields, like chemists or condensed matter physicists, and tell them you have this formula that the entropy is proportional to the area, that looks very puzzling, because usually entropy is proportional to the volume, an extensive quantity, not the area, and usually it's proportional to the number of degrees of freedom somehow that you've put into the system. So if I had 3 or 4 more neutrino species, I would expect the entropy of the system to increase proportional to those number of species, but the Bekenstein-Hawking formula, of course, doesn't have any room for that. It's given purely in terms of fundamental quantities. The other thing you should do while we're doing these elementary exercises is put in numbers and recognize how big this entropy is. I'll put that in the next slide. Again, thinking in terms of physics of other systems, this temperature is very small, as you know, and so this system is cold. It's thermal, but cold. On the other hand, in the same limit that the temperature goes to 0, which means a very heavy black hole, or h bar going to 0 formally, just because I've multiplied and divided by h bar, as the temperature goes to 0, the entropy goes to infinity. So that also sounds strange to most other physicists. How do I have a cold state which has essentially an infinite number, a very, very large number of degrees of freedom excited in it? As Stephen himself pointed out in the 70s, the energy, since the temperature is inversely proportional to the mass. Mass is energy, so energy is inversely proportional to the temperature, and therefore dE dt is negative. Now, again, if you open up standard thermodynamics books, in fact, going back to Einstein himself in fluctuation-dissipation relations, the dE dt is essentially the heat capacity of the system, and that for any stable ensemble is just related to the energy fluctuations, E minus E bar squared. So it's positive. So how does it become negative here? And in fact, if you look at the, not just the sign, but the magnitude, it's supposed to tell you, in other systems, it tells you something about the time scale of which things can go unstable. And this time scale is basically nothing else but the dynamical time scale, the light crossing time of a black hole. So this looks also very strange if you think about ordinary thermodynamics. One can ask, can equilibrium thermodynamics be applied at all to this system? Then we, of course, have the information paradox, the question of whether information disappears, mixed states appearing from pure states, unitarity, where is this information stored? And standing in the back of all of this somewhere is Ludwig Boltzmann with his this epigram on his gravestone, asking, well, where's my formula? How did you count the states? The logarithm of what quantity is this entropy? So these questions remain. I think after all these years, we've had a lot of suggestions, but I would say, to my mind anyway, no definitive answer. So let me just do a very simple-minded argument. Again, this is very simple, just to give you try to keep things at a very basic level to start with. If I try to estimate the entropy of a self-gravitating system, either in the microcanonical or the canonical ensemble, it doesn't make any difference for a large enough system, then the simplest thing to think about is something like black body radiation. And again, just order of magnitudes, the energy is the volume times the temperature to the fourth, the Planck law, Stefan Boltzmann constant here, and the entropy is going like the volume times T cubed. So I can eliminate the temperature if I don't know what the temperature is, and I write the entropy in terms of the volume and the energy this way, just do the simple math. And the volume is, of course, going like the radius cubed, so I get this relation. And if I think this is a self-gravitating collapsed object, the energy is the mass, and the radius is the Schwarzschild radius, then I immediately get the entropy is going like the 3/2 power of the mass. And in fact, if you look at Zeldovich's book, Zeldovich and Novikov, that is the entropy of a relativistic star. A star of a mass of about 50 to 100 solar masses will be dominated by its radiation pressure, and this is its entropy. This is a bigger entropy than the entropy of the sun, because the sun is a main sequence star, which is, its particles are not relativistic. It's not dominated by its radiation pressure, and the entropy is less. Anyway, this looks like a kind of a maximum that you can get from relativistic relations. It's a 3/2 power. So here's where you put the numbers in. The Bekenstein-Hawking formula going like m squared. Again, it's m over m Planck, square root, that's the difference between these two. And this is a factor of about 10 to the 19 for a solar mass object. So somehow one is supposed to count up the number of states and get the logarithm of the number of states to be 10 to the 19 bigger than what you would get by a naive back-of-the-envelope calculation. Granted, this is naive, but it shows you how far you have to go. Okay, so now go back again to first principles and think, are we sure that this is what's going to happen? And of course, the basic foundations of black hole physics were laid in the 60s, and Stephen and Penrose, Roger Penrose, were very influential in that. And the famous singularity theorems were proven at that time, that Penrose, for example, back in 1965, proved on very general grounds, if you assume the weak energy condition and the trapped surface forms, then there will have to be geodesically incomplete geodesics and therefore presumably a singularity. However, this is violated, we know, by quantum field theory. For example, Casimir effect is an example which doesn't obey this energy condition. Stephen and Penrose proved another version of this using the strong energy condition in 1970. And this is a very interesting energy condition because, again, it seems pretty reasonable for most matter. However, we know that this is violated, for example, by dark energy. And now we're more comfortable thinking about dark energy. It seems to be there in the universe. If you think about inflation, it has P equals minus rho, and this quantity is less than zero rather than bigger than zero. It's somewhat less well known, I think, in this community, but a fact that even in hadronic physics, if you look inside a hadron, inside of a proton, there is a vacuum energy. It's, of course, negligible gravitationally, but it is a P equals minus rho condensate due to the gluon condensate in QCD. And so there's another very well-established example in which this energy condition is violated. So the important point is that you, again, will get a black hole forming if you have certain conditions on the energy momentum tensor. You can't say anything unless you say something about T mu nu. And it was pointed out really a long time ago in the 60s, prior to inflation, really anticipating what we now call inflation, by Zeldovich and Sakharov in the Soviet Union, that if you had a negative pressure vacuum-like energy equation of state in the early universe, then you would avoid the initial singularity. So they were thinking, both Zeldovich and Sakharov were thinking about singularities in the early universe and also in gravitational collapse. And there's, of course, a great similarity between them. And therefore, if you had negative pressure, you would not have the initial singularity. And Sakharov and then Glynner realized that if that happened inside of a collapsing object, it would defocus geodesics and you would have an effect of repulsion. So the same effect which is causing the universe expansion to accelerate could actually eliminate singularities in a collapsing object. So I won't trace all the history, but basically in the early 2000s, we were thinking about analogies between gravity and condensed matter physics, thinking about all these issues with black holes. And again, I'll give you a naive heuristic argument, and then I'll show you some results. I want to get to the Schwarzschild solution, which is really curious. If you think in a sort of naive physical way, then gravity is a theory of bosons. It's an attractive interaction between them. Interactions may become strong. There are various ways of looking at this, but even a very weak interaction generally leads to some sort of condensation phenomenon in other systems. So it's not, I think, totally crazy to think there could be quantum correlations which lead to the formation of a condensate in gravity, in the same way that you have interactions that lead to superconductivity or superfluidity. If there were such a thing, what would it look like? Since we don't have the full theory, we're just trying to argue in physical terms. Well, if you have an order parameter, and the order parameter is a scalar, we want to be consistent with general relativity and general covariance, so it has to transform in a simple way. Let's assume it's a scalar. Well, you already know the answer now from inflation, right? If you have any scalar like the inflaton with a potential, and its spatial time derivatives are negligible, then that just enters the Einstein equations as P equals minus rho, as an effective cosmological term. You then look at the Gibbs relation, which is a general relation for entropy, density, and pressure. And if you have no chemical potential, then the Gibbs relation looks like this. So it tells you if P equals minus rho, you expect this to have zero entropy density. Okay, and indeed that's true in other systems. But zero entropy density means you have a single macroscopic state. You have a coherent state where the log of the number is 0. And therefore, this is a condensate. If you have p equals minus rho, it can be reinterpreted as a condensate in these condensed matter terms. And as we just said, if p equals minus rho, p being negative, then this energy condition is violated, and you can have a repulsive core. So a condensation of any kind that produces this, as Sakharov and Zeldovich were thinking of back in the 60s, would lead to a repulsive interaction, and as far as the gravitational forces are concerned, and you could end up with essentially a bag, a self-confined condensation in which the trap is gravity itself. And so we call this idea a gravitational Bose-Einstein condensate, and these are, again, just general physical ideas. I want to show you how it's realized. So we proposed this back in 2001, and now today I'm going to talk about how this can actually be shown to come about in Schwarzschild's second paper. So you know he wrote 2 papers in 1916 before he died. One of them is the famous exterior solution, we all know, but he also looked at the interior. He didn't know how to solve the equations, so he assumed the simplest thing, which was constant density. So let's go back and look at static spherical symmetry. There are 2 metric functions in general. I call them f and h, you remember from the metric. And I can always call h in this form, where m of r is the Misner-Sharp mass. The energy momentum tensor for spherical symmetry it has 3 functions in general: the energy density, the radial pressure, and the transverse components of the pressure, which need not be the same as the radial one. And you write down the Einstein equations and the conservation equation. This is basically just pressure balance. And you get 3 equations for these 5 functions. So it's, of course, not yet determined. Now, before I go to the Schwarzschild case, there is a very important and interesting theorem proven about that set of first-order equations by Buchdahl back in 1959. So he made essentially the same assumptions, that there's a static killing time. He's looking for a static solution, spherical symmetry. He assumed isotropic pressure, so he did put all the pressure components equal to each other. That eliminates one of the unknown functions. And then there's only one unknown left. And you can then prove that if the energy density is a non-increasing function of radius, d rho dr less than or equal to 0, then, and you also have continuity with the surface of the star, assume everything is continuous at the surface, and you match onto the exterior Schwarzschild solution, then one can prove a theorem, which is that the radius of the star, I call capital R, has to be bigger than 9/8. This number comes out, 9/8 the Schwarzschild radius, or the pressure diverges in the interior. This is a necessary condition for the pressure not to diverge in the interior. And the interesting thing about this is that this 9/8 is, of course, bigger than 1. So this issue of what happens to the pressure inside is taking place before you reach the Schwarzschild radius, before it's a black hole. This is still just a static star. Whatever the equation of state is, that's why this is a powerful theorem. It's assuming spherical symmetry, of course, but whatever the equation of state is, you have to have the radius be bigger than 9/8 the Schwarzschild radius, or you don't have a static solution in which the pressure is everywhere finite. So let's look at the case which saturates this bound, which is the case where d rho dr is equal to 0. In other words, rho is a constant. Well, that is what Schwarzschild did back in 1916. He looked at the case of a constant density interior, and I just want to emphasize that this Buchdahl bound says that under adiabatic compression, so I imagine I have a sequence of stars, all of which are static at different radii, no matter what the equation of state is, again, this has the same features as the singularity theorems. No matter what the equation of state is, quite generally, under these assumptions, something has to give at the central pressure. before I reach the horizon under this adiabatic compression. So I'll just go through the Schwarzschild solution because it's interesting to see what you get. This is in textbooks. It's in Bob Wall's book. It's in Weinberg's book. And this is what the solution looks like. It's a very simple equation you have to solve, which is that pressure balance equation. And you get just this ratio of square roots, okay? Very simple. H of R is like this. This is a constant density, so the Misner-Sharp function is growing like R cubed. It becomes equal to capital M at the radius, capital R. And you notice something very curious about this, that as long as capital R is bigger than 9/8 again, this denominator here never vanishes on the real axis, and it's a perfectly reasonable solution. But when you reach this magical value of 9/8, then this denominator vanishes, first at the origin, and that's usually enough for people to then stop talking about it. That's what happens, for example, if you look at the textbooks. But we went further and said, okay, let's just keep going. Suppose the radius is smaller than 9/8. What happens? What happens is that this 0 moves out from the origin and becomes, at a finite radius, R0. Okay? So if R is less than 9/8, this R0 is greater than 0. But you see, as R approaches the Schwarzschild radius, this becomes the Schwarzschild radius from inside. So as I push the object from the outside, beyond 9/8, within 9/8, the Schwarzschild radius, this singularity of the pressure starts at the origin and then grows outward. And at the point at which the exterior radius is the Schwarzschild radius, at that very point, this singularity goes to the Schwarzschild radius from the inside. So what's going on? So should you just throw this out? Well, that's what most people did. We just went back and looked at it. And the interesting thing is that the other radial function, the other metric function, f of r, which is the redshift factor, GTT, this is proportional to the same denominator here squared, which means it vanishes at the same place, and it's always positive otherwise, other than this one radius. And moreover, because this is just a simple difference of square roots, what happens is that a new solution opens up inside, which has negative pressure. So this just changes sign, and inside this radius, the pressure becomes negative. This is just following the algebra of Schwarzschild's solution. So you can plot this and just play with it and see what happens. So for greater than 9/8, the pressure is very reasonable. Nothing is happening. But as you increase, as you approach 9/8, what happens is this pressure at the origin starts to diverge. Okay? The central pressure blows up. And as you go beyond 9/8, this central pressure that blows up at a finite radius, and inside that radius, you have a negative pressure region. And moreover, as R goes to the Schwarzschild radius from above, R0 goes to the Schwarzschild radius from below, and the negative pressure region just fills up the whole interior, and in fact becomes P equals minus rho. Just a feature of the solution. Okay, so this is the metric function. It has a cusp-like behavior because f is d squared, the denominator squared, so it's always positive other than this one point, and this point moves out in the same way as that place where the pressure is diverging. So the redshift factor has this cusp-like behavior, and now you can ask what happens for all of these sequence of solutions, what happens also in the limit. So in the limit, you get, as I say, P equals minus rho interior, you get a static patch of de Sitter space. The only thing that's curious is that instead of time, usual static coordinates of de Sitter, f is equal to h, but in fact here f is equal to 1/4 h, and this will turn out to be important. So it's nothing else but a coordinate reparameterization of the interior time, but the interior time is not arbitrary, it's fixed by the boundary condition at infinity. It's the same t that goes to Minkowski space in the asymptotically flat region. Okay, so time runs slower inside. And now the important thing to look at is whether or not this singularity is a reason to throw things out, or what it actually means. Well, for that, you look at the Komar mass-energy flux, which is basically the analog of Gauss's law for a static geometry. So you can write, you can define the surface gravity this way, and of course it becomes the ordinary Newtonian acceleration far from the black hole, but otherwise it's given by this, and this object obeys this equation, which is the analog of the Poisson equation. So you see that all of these terms in the stress tensor act as sources for it, and this very particular combination of metric coefficients. And now what is important is, at the same point that the pressure is diverging, like 1 over the denominator linearly, the F, you remember, is going like d squared, so square root of F is going like d, so this cancels. So this is totally integrable. The Komar energy is integrable, even through this singularity. And what's going on there is that there's a discontinuity because of the cusp. There's a discontinuity in this quantity, which you can think of as generating a transverse pressure. So however you look at it, when you look at the discontinuity in the derivatives of the surface gravity, that leads to the conclusion that you cannot maintain a isotropic P equals all the P's equal to each other, but the transverse P has to be different from the radial P. And the difference is just localized at one point, which is where this cusp is by the discontinuity in derivatives. So this is just a boundary layer. It's a delta function boundary layer with a surface energy, because of course the delta function is integrable, which is equal to this for the general case. And as R naught goes to R, this just becomes twice the mass of the object. So what is going on is that, of course, the total mass is fixed by the exterior boundary condition. What is going on is that you're just distributing that mass in a different way between the volume piece and the surface piece as you vary the total radius, as you vary R naught. And at this limiting case, in which you have the Schwarzschild radius, this is minus m and that's plus m, so that the total is just, again, m. Okay, now you go look at the surface gravity, and it's discontinuous, just coming from this discontinuity in F. And the discontinuity can really be interpreted as a surface tension now. And that's what my remark yesterday after Malcolm's talk, that in this case, at least, there is sense to talk about the discontinuity in the surface gravities as a surface tension. This is a real surface tension now, because I have a transverse pressure. So it really is the surface tension of the surface. And of course, because of this cusp, the interior is not the analytic continuation of the exterior. And so you can now go through the same argument of Jim Bardeen, Brandon Carter, and Stephen back in the 72 or so, and look at the infinitesimal form of this. You just go through the same steps, and you see that you can write the total differential of the mass energy as a volume term and a surface term. And this now really is a surface tension. So it's not the surface gravity itself that should be identified with the surface tension, but the discontinuity in it. And this essentially generalizes the SMAR relation from the case of a black hole to the case in which you have this interior condensate. And I remind you, this really should be thought of as a condensate because it has no entropy. So the Schwarzschild interior solution actually describes, in this limit, in modern terms, a zero entropy, zero temperature condensate. The discontinuity in the surface gravity is non-analytic, is really the surface tension, not a temperature in any sense, and the surface area is the area, not the entropy. This just has a classical mechanical interpretation. I don't have to divide or multiply by h bars. There's no Boltzmann's constant in this. It's just classical mechanics applied to this relativistic self-trapped system. Okay? That just comes out. I also mentioned that one can change the coordinates and write the solution globally this way, introduce a new radial coordinate called C, which is just defined in terms of the radius this way, such that the surface is at c equals 0, but you notice this is a Rindler-like form. If I expand near x equals 0, where this is 1, q is near 1, so it looks like Rindler space. However, it's crucially different from Rindler and flat space, because c squared does not change sign as I go through x equals 0. C is just a radial variable which remains real, and for interest of people who know about junction conditions, this actually serves as an example to generalize the Israel junction conditions to a null surface. So this is a perfectly reasonable boundary layer, which is C1. In other words, the metric and the first derivative of the metric are continuous, and the discontinuity in the second derivative is just measuring the transverse pressure and the surface tension. So I would say this is faithful to Einstein's equivalence as he originally conceived it for real coordinate transformation. There's no analytic continuation here. Curiously now, you can look at the geodesic equation and just see what happens to null rays as they strike the surface, and they go through. So you can just match the geodesics on interior and exterior, and because the interior is a region of de Sitter space, you can just find the angle of refraction, and it acts like a material which has a index of refraction less than 1. In other words, it bends the rays away from the normal. So it defocuses rather than focuses. So if you look at a series of null rays, this cartoon will show you that they basically, an image will be, it acts as a defocusing lens. What is that called? A concave lens, I guess. So that if there's an object behind here, it's actually going to defocus it. This is, of course, completely different imaging characteristics from a black hole, which would absorb the light. On the outside, the rays are going to behave just like the black hole because the exterior is Schwarzschild, but if the rays penetrate, you get a completely different picture. So this idea that we had of an interior condensate is in some sense realized just by pushing it a little harder with modern techniques, is realized in the interior Schwarzschild solution. And you can now look at this relation and ask yourself various questions, like, well, this is just a delta function layer at this point, but notice it's very important that the surface tension came out positive. That's the way it came out. And that means that the energy is minimized by minimizing the area for fixed volume. This is, there are actually two canceling signs, but it comes out the same way as it does for an ordinary soap bubble. Okay? A soap bubble is stable, it has small oscillations, but it's stable because if I try to change the area, that costs me energy. And here, the same thing. The surface tension comes out positive, so that if I try to change the area, keeping the volume roughly fixed, that's going to cost me energy, and therefore I expect the system to actually be stable. The surface tension acts as a restoring force. So it's of course now an interesting question to try to go beyond this and calculate the small fluctuations, but just heuristically, the characteristic frequency has to be the same frequencies that Klaus Kiefer was talking about this morning, basically of order of magnitude of the quasi-normal mode frequencies, which means that this would be a striking signature. If we could observe such objects, then it would be have a discrete gravitational wave spectrum. So the situation here is, curiously reminiscent of the Bohr atom, right? Classically, of course, electrons fall into the Coulomb potential, and matter would be unstable. But matter is quite stable, and ultimately that's because of quantum mechanics, because of the uncertainty principle. So here, the suggestion is that quantum mechanics again comes to the rescue and produces a condensation phenomenon which would stabilize a black hole, so things don't fall in, and just like the Bohr atom has discrete frequencies, this object should have discrete frequencies. So this is a potentially observable signature to test the idea. So a bunch of remarks. You should tell me. Time's up? Okay, if time's up, I'm just going to end with a slide or two. I was going to try to discuss how one could realize this now in an effective theory, but let me just make a few remarks and I'll stop. So first of all, the non-analyticity is very similar to what one would guess in condensed matter physics. So people like Bob Laughlin and Chaplin had similar ideas, but rather than talking about an analogy, this just is coming out of the solution of general relativity in the Schwarzschild solution. So because the killing vector is everywhere time-like, except possibly at one point, a Hamiltonian exists. If the Hamiltonian exists, and its emission with proper boundary conditions, it should certainly, for any field put on this background, describe unitary evolution. I also mentioned that because things are non-analytic right at the surface, there's no reason to demand analyticity of Green's functions, and so one would expect that the quantum state of a test field in this background is more similar to the Buller state. It doesn't have to be exactly Buller, but similar to it than it is to, say, Unruh or the Hartle-Hawking state. Of course, in such a state, the energy density is again negative and violates the weak and strong conditions. Now, what I was going to talk about next, I'm out of time, is putting quantum effects into this. This is, of course, a very simplified model. If I now put h bar into the system, I expect that this infinitely thin boundary layer is going to get regularized by essentially the Planck length divided by a small parameter epsilon, Planck length divided by the Schwarzschild radius, and that will mean that the physical thickness, because of the metric factor, the physical thickness is going to be the geometric mean of the Planck length and the Schwarzschild radius, which is quite a bit larger, of course, than the Planck length. So one might still be able to think about this in an effective field theory approach, very far from Planck scale physics, although you do need to put the Planck scale in at some point. So this epsilon will regulate this behavior, this cusp, and round it out. Okay, so this is the effective field theory. I'll mention just another side remark is that if you look at the bag constant in QCD, it's got a number something like 75 MeV per Fermi cubed, and so this should be going on inside a neutron star if you start approaching the Oppenheimer-Volkoff limit, and the density, just from my simple constant density Schwarzschild solution, is this value. So for a mass of a few solar masses, this is within about an order of magnitude. So you could even imagine that QCD itself, gluon condensation, and the bag constant is actually generating this interior P equals minus rho condensate, but you probably need more than that, and then you have to do gravity itself. So that's where I was going to go next. I'll skip it, unless you have questions, and just sum up. So the Buchdahl-Bahn tells us that under adiabatic compression, interior pressure divergence develops before the event horizon. The constant density interior solution saturates this bound and shows the generic behavior. Put in your favorite equation of state. It just means something is going to happen before you reach 9/8, a larger radius. It's very important that the infinite redshift takes place, or blue shift takes place exactly at the same point where the pressure diverges. The Komar integral is integrable as a delta function singularity, a non-singular interior, and the differential form then of the energy is just nothing else but essentially classical mechanics generalized to relativistic system of a mechanical surface energy and not entropy, at least in this realization. And of course, there's no problem with unitarity or quantum mechanics, and the information paradox just poof, gone away, okay? And this is already there in the Schwarzschild solution, and so our suggestion is nothing else, that this could be the cold quantum final state of gravitational collapse consistent with quantum theory and general principles, and I would like to show you a little more of how I can do that in a more in a fuller theory, but maybe I should end here, and one can start speculating about what this might mean for astrophysics. And it's very curious and interesting that one might be able to tell this apart from black holes by both the gravitational wave signals being discrete, by imaging, and as you know, we've already discussed, there is the possibility, very exciting in the near term, next few years, of actually imaging the central object in our galaxy, Sag star, with the Event Horizon Telescope. So the provocative idea I want to put out there is that black hole and dark energy problems are related, and maybe it's the same mechanism that solves both problems. Thank you.